This is basics integration rule part 2. As we discussed earlier in part 1, these are the very important and common integration rules. Okay, the arcsine, arctangents, and the natural log. So let me illustrate with these 3 examples down here. So look at these 3 examples at once. So what do you see? The number 1 here, you have 3x squared minus 5 over x cubed minus 5x. You have x to the 4th over 1 plus x to the 5th. And then you have 1 over 1 plus 8x. If you look at all 3, they might not be the same, right? But they are similar in many ways. The first thing you should notice, they are rational functions. So rational function means polynomials to second degree over third degree, fourth degree, fifth degree. This is 0 over the first degree polynomial. Okay. Now, if you observe carefully, the top is always 1 degree less than the bottom, right? 2, 3, 4, 5, 0, 1. Now, when you see these, we can try the following. You always try the first when you have rational function like that, where the numerator has 1 degree less than the denominator. Now, why? Because you can basically check. What I'm trying to do is trying to apply the formula here, that box in red, u prime over u. If you have the top is a derivative of the bottom, the denominator is u, the numerator is u prime, then you can take a derivative of this. Okay, integrate this, and then you have an actual log absolute u. The first one, if you look at this, 3x squared minus 5, look at x cubed minus 5x. So what I do is I'm going to look at the denominator. Okay, the denominator. What's the derivative of x cubed minus 5x? X cubed minus 5x. Well, I take derivative of that, it can be 3x squared minus 5. You see that the denominators, you take derivative, it's going to be numerators, right? So if this is your u, then your numerator is u prime, right? So that basically matches formula, and your answer will be natural log of absolute of the denominator x cubed minus 5x plus c. Done. You see how fast it is when you have recognized formula, so make sure you learn how to do that. Although you can do without, I think you can do without this using substitutions, but they'll be comes in handy and make things a lot easier if you know how to do that in a single step like I did here. Okay. Now the next one. If you look at the number 2 here, you have x to the 4th over 1 plus x to the 5th. It's similar. I will check by looking at the denominators. What's the derivative of the 1 plus x to the 5th? It's 5x to the 4th, right? 5x to the 4th. The numerators have x to the 4th. So what I want is if you have 5x to the 4th on the top, that would be perfect, right? If you have 5x to the 4th, it would be perfect. It would match a formula, but we don't have it. Using the same classical, or say, standard techniques. If you need a 5, you can multiply by 5 and times 1/5. That introduce this. Now you can follow the formula. This is 1/5, and then you have that's equal, and we see that u prime over u now, it can be the natural log of the denominator. Okay, and that's it. We're done. Okay. Again, if you don't see that, you might have to use the substitution rule, which takes a lot of time. Okay. The last one is the same. what's the derivative of 1 plus 8x? What are the denominators? Okay, so the denominator I have 1 plus 8x is 8. So because I'm equal to 8, I do need an 8 on the numerators. Okay? So I need the numerators to be 8. Again, so I'm going to use that same techniques. If you want the 8 on the top, all I need is multiply by 8, right? Instead of 1, you times 8. How about 8? Now you have 1/8 in front, and then the integral now fit the formula, and that is u prime over u. So that is the natural log of 1 plus 8x plus c, right? So yes, that finished the these three problems. They all use the same formula, natural log, and make sure that you learn how to recognize it. Okay. Okay, so the next example here, okay, look at it, some color. Okay. The next set, 3 example. Now look next 3 examples here, 4, 5, and 6. They are very similar. See, look very similar. They are also rational. Okay, polynomial, polynomial. Now, what's the difference? So you see this degree 0 over 2, this degree 1 over 2, this degree 2 over 2. Okay, so different. Now, out of these 3, the one that could use a natural log, you probably view that we use over here, which one? Number 5, here, right? Degree 1 over degree 2. Because when you take the derivative of the denominator, it's gonna be always 1 less. So the 4 and 6, you cannot use the natural log, but number 5 you can, right? Definitely you can. I'm going to go with number 5 first because I could use that same formula that we did up there, right? So again, what's the derivative of x squared plus 4? It's 2x, right? You take the derivative of this, you got 2x. And so what you want is you want 2x instead of 5x. Now, to modify, we will use the same techniques, but there's an extra 5 there. Well, when you have an extra constant, you always take that out so to make things easy to do. So you take the 5 out here, right? And then you still have an x inside. What I need, this is x squared. I need 2x. Standard techniques, times 2 divided by 2. And now your constants outside is still 5 over 2, right? Still have 5 over 2. Now what inside is the u prime over u, so it's a natural log of absolute of x squared plus 4 plus c. Okay, so that is the answer. Okay, so I have, see very quick, if you can recognize that formula. Okay. Now, if you look back at number 4, then how do we do number 4? Well, for number 4, 5 over x squared plus 4, you see that's x squared, that's 4, that's 2 squared. Does it look familiar? Here. You see there's 1 over a squared plus u squared. So that formula is the one we're going to use here, right? X squared plus 4, not 4 plus x squared, right? So the same. Now, well, this is the 1, and I have the 5. Well, I can always take that out. So basically, that is the arctangent rule. So make it crystal clear, I'm going to rewrite it by take out the 5. So that's left with a 1. again, to make it crystal clear, I swap the order. 4 over here plus x squared. So you can see the formula we have is 1 over a squared plus x squared, right? Or a squared plus u squared. So the answer is 1 over a, arctangent of u over a, which is, you have the 5 and 1 over a, what a in this case, 2, right? So 1 over a is 2, and you have arc tangent of x over a, again is 2, right? So that's plus c, and that finished the number 4. Okay, that's 5/2 arctangents of x over 2 plus c. Okay. Now, last one here, number 6. For number 6, you can see look very similar. See, they look similar, but here's the degree 2 over degree 2. Now it's gonna be very different. It cannot be the log, cannot be the arctangent. This one actually has 2 ways to do. You can use it as a trick. You can do it quick, or you can use, well, you can see the substitution, in fact, doesn't quite work. If you let u be x squared plus 4, you can try. But this one I'm not going to focus on, just give a hint. So this one will be tricky. When degree, the top and bottom is the same, you can try to make it work by rewrite it this way. So basically, I do the long division. We're going to go over that in the next sections, I think 2 or 3 sections. But for now, this one, what I'm going to do is I am going to plus 4, right? So instead of x squared plus 4, and then you see that 5x squared plus 20, basically add 20 and then subtract 20. And that's over x squared plus 4, right? So that's a trick there. You see the top is the same as that one, right? You multiply it out and cancel out. The reason I want that is because I want to separate that into two fractions, right? So this is first fractions. This is the first fraction. Now if you simplify, this becomes just 5, and then minus the second fraction is 20 over x squared plus 4. Okay. And this way I can integrate this. Well, that one is 5x. That one is 20. So you see that one is similar to this one. It's just a arctangent. So that's 20. That's over 2 times arctangents of x over 2 plus c. Or if you simplify, it's really 5x minus 10 arctangent x over 2 plus c. Don't worry about this problem if you don't know why I'm doing that trick at the beginning of the problem. We'll go over that in detail in I think 8.4, I believe. Okay. So that finished the this set for 5 and 6. Now, finally, if you look at these 3, I can label that 7, 8, and 9. So these 3 problems, actually a bit, 7 and 8 is actually together very similar. 9 is very different. This one actually is an easy one. Just want to let you know, kind of throw that problem in so you can recognize that when you find the antiderivative cosine, we're going to use this quick formula, which is the one I have up here. Cosine of ax plus b is 1 over sine of ax plus b. So basically what it means is What's antiderivative cosine? Well, it's going to be sine, right? Antiderivative cosine is sine. However, I have sine at phi plus 3. So when you take the derivative, you times phi, we do the antiderivative, we multiply by 5, we'll times 1/5. So that'll be 1/5 sine phi plus 3 constants plus the constant there. Okay. And that one is that. Okay. Now, these two are a bit harder. In fact, I'm not going to go over these. The reason it's harder because this one you have a polynomial, so trinomial down here, where if you like this one, when you see that the square, we attempt to use one of these two actually. Right, this one is sum of squares. That one is basically u prime over u, but it doesn't quite fit the form. So number A, you required some tricky because I see degree 1 over degree 2. So that looked like the u prime over u worked, right? So if you look at the u in the bottoms here, x squared plus 4x plus 8. If you take a derivative, you got 2x plus 4. So the trick here is, in order to make it work, you have to modify the 5x to become somehow you have 2x plus 4 on the numerators. Okay, and that will be very tricky, right? I'm not gonna go over here. So leave it just intention, that's what we do. So you have to modify somehow, you end up with 2x plus 4 there. So like if I have times 2x and something, you subtract. So you can make that look at 5x, okay? Now this is the one where it doesn't fit the u prime over u, and so we have to use the a squared plus u squared. But in order to do that, you have to put it on what we call completing square. So we call completing square, you have x squared plus 4x, right? So what constant do we want here? Half of 4 is 2 squared, you got 4. So basically plus 4, right? So you need plus 4. So I'm going to write a as plus 4 plus 4. So that way this will turn into an x plus 2 quantity squared plus 4. And now this integral would become 5 over x squared, x plus 4, sorry, x plus 2, x plus 2 squared plus 4 dx, right? So that's on the side. Now, in order to do that, finish here, you have to use a substitution, let u be x plus 2, and du is dx. So that way, you would have a u squared plus 2 squared, and then apply the arctangent formula, right? I'm going to stop right here, and that finished 8.1.